Looks like enough people are here anyway, so we should go ahead and get started. I'm Mr. Younger. I'll be teaching your Physics 241 this semester. I'm sorry about it being by flying by the seat of your pants, giving you a invitation first thing this morning. Uh, for a class that meets today, of course, that is at least you guys are scheduled for that, so that makes more sense. I even screwed up worse on my 242 class in that my 242 class is supposed to meet tomorrow, but I accidentally sent them the same text message I sent you or same announcement I sent you. So, anyways, we are going to meet every Monday and Wednesday from 5:30 p.m. to 6:50 p.m. I'm also on the tail of that offering an office hour that should begin. Well, people other than you guys that are logging in should log in by 6:35, and then I'll stay maybe as late as 8 o'clock on a given night. Some nights I might not be able to, but that's generally what my plan is. But they're completely open question and answer sessions when no one has any questions, and I just log off. So if you want to come to those office hours, make sure you do it. You guys, since you're meeting on Mondays and Wednesdays, there's an identical class. It's actually a different class. It's 242, but it meets at the same time as yours. So you will have an office hour on Tuesdays and Thursdays, just like the one on Mondays and Wednesdays. So you can log in no later than 6:35, 6:40 at the latest. And then you can ask me questions when class is over. So you have that office hour as well as the office hours that are in the morning on campus and any ones you might want to make via reservations or Zoom meetings or reservations on campus. So uh, we are as I told you, I am teaching Physics 241, what we call University Physics 1. The book that we're using is Giancolli's fifth edition of Physics for Scientists and Engineers with Modern Physics. Okay, because ideally 241 ends after we do chapters 1 through 11. Then we jump to 14 and then 15. And then ideally, if we have time, we jump to 36, which is special relativity. If we had even more time, we'd go into particle physics. But then the 242 course goes from chapter 17 up to at least 30, but ideally 31, and then 36, or excuse me, 37, 38, 39, and maybe cosmology. But of late, I haven't been able to fit in the quantum mechanics that comes from chapters 37, 38, and 39, nor have I been able to fit in cosmology or nuclear physics. But that's the ideal scenario. We're going to work at roughly a clip of one chapter per week. It's a little bit higher than one chapter per week because we're going to cover, obviously chapters 1 through 11. That's 11. Then 14 and 15. That's 12, 13. And then 36 would be 14. And we have to have test days. So in principle, we need to be able to do a little bit more than one chapter per week. I'm going to attempt to do that in such a way that I cover the most complicated issues within a given chapter, and some of the simpler stuff I leave for you guys to figure out on your own or figure out from my YouTube videos, so that we can keep the pace. But I'm not going to talk too much about the syllabus right now. I'm going to go ahead and make a video on that, so it'll explain the syllabus in great detail. But you can also go ahead and read it. I just posted a updated version. There was one posted earlier this morning that was missing some of the some of the class schedule. I just repaired that, put in the rest of the class schedule that was meeting. It's up there now, so you can look at it. Let me see. Anybody have any questions so far? One thing I'll tell. Yeah, go ahead, Isaiah.
Sorry, I came in a little bit late. Did you go over any of the lab stuff yet? Like as far as like when lab is gonna meet up?
No, I had not done that yet. In fact,
Okay.
I'm trying to look for how exactly I'm going to do that. I haven't quite worked that out yet, but I should be making that decision. Ideally, what I would like to do is have you guys text me and let me know of any times you might have that might be convenient. It doesn't have to actually be a face-to-face meeting, but I'm going to once a week go on and post a video telling you how to do the lab, and then you can do it. Uh, but if I make it a time that's convenient to you guys, then y'all could actually show up, use that for time to get help on the lab. But generally speaking, they don't have to do it. So, assuming you're taking my lab, there are some students that are taking a different lab. That would be under an entirely different instructor. So I'll keep you posted on that. Think that's a good question though, Isaiah. Anybody else have any questions? I'm going to go ahead and type my email address here just because it is in the syllabus, and obviously you can always get it there, but I just wanted you to know that's my email address. I just chatted it to everyone. When you do email me, there's three rules that you got to follow. The first one is you only can email me from your TCC email account. So only do that, or I'm liable to not see it. The second rule is make sure you start the subject line. That means even if you hit reply on an email I send you, you still have to click into the subject area to the left of that, and then type in 241 space night, NIGHT. That has to be the beginning of your subject line or it will not be seen. And then the third one is in your email, you need to state your first and last name. That's also true about when you send me text message. So if you need to text me, which I did give you my cell phone, I'm getting ready to put it on here in the chat as well. But if you text me, I want to make sure every time you text me, you give me your first and last name and what class you're in. So keep that in mind because I really communicate with a lot of people. And though I sort of remember conversations pretty well, if I've had 20 of them, I'm obviously going to mix up one. So it's best if you include that. That being said, here is my phone number. That's also going to be on my syllabus. I just don't want to show that, of course, on the internet or anything like that. And this video, of course, will be going to my YouTube channel right after class. I normally try to do it the same night, but sometimes I can't do it till the next morning. It all depends on bandwidth, exhaustion, that sort of thing. So rule one was only your TCC email. Rule two was 241 space night for the subject line, at least the beginning of the subject line. And rule three was first and last name. Thanks for that, Michelle. Any other questions, anyone? Now, the reasons that you go about texting me are one, if you have something that's time important, like maybe you're meeting me for a test or something like that, or you set up some kind of Zoom meeting with me and something's come up, that's a good time to text me because you can just send me a text and say, "Hey, I'm running late," or "Hey, I'm not going to be able to make it." That's perfectly fine, and I always expect that. And don't worry if you send me an email. This other variety, if you send me an email late at night, it's not going to matter. I have my phone set up where it won't wake me up if I'm already asleep or something. So send me text messages as late as you want to. The other reason for sending the text messages, ideally, is if you email me and you don't see me send you a response email, or you don't see a announcement posted in Canvas or an email to everybody that answers your question, then you would know, oh, he must not have seen my email or something like that. If it's been a whole business or slash school day and I still haven't replied, then you should text me and talk to me. Okay. Now, what a full business day means is if it's a regular Tuesday and Wednesday where there's no holidays, if you send me an email at 12:01 a.m. on Tuesday morning, then I have to send you a reply by 11:59 p.m. and 59 seconds on Wednesday. If, on the other hand, again, no special Fridays and Mondays, but if, on the other hand, you send me a text message at Friday just after midnight, 12:01 a.m., then I need to reply to you by 11:59 and 59 seconds p.m. on Monday. So that's what a single business day response is supposed to look like. So if you ever send me an email and you don't get a response, first check your announcements to make sure I didn't post the answer to your question there, because if I get 10 15 students that all ask the same question, I don't want to write 10 or 15 emails. I'm just going to write one email to everybody. So check your announcement. I normally do it in the announcement, and then the announcement goes out as an email, so that handles both. But you also might want to just check your email. So either one of those should work, or both of those really should be what you do. Once you find out that I haven't answered your question, then go ahead and text me. I'm not going to get upset if you text me at other times, of course. It's just a matter of I might not be able to afford the time to answer you as quickly, because normally what happens if I'm awake when you send me a text message, I normally reply within minutes unless I'm in the middle of class or something. So What we're starting off with, again, I'm gonna give you a video that explains the syllabus, so I don't want to waste any quote unquote waste any time covering the syllabus except via video. But tonight I'm just going to start working on chapter one. Benjamin has a question.
Yes, sir. I have a question. Sorry, I kind of joined not too long ago. I had a question about the lab because I didn't see the content on the canvas.
Yes, the content's not up yet. Actually is being loaded up, but it takes a little while. So it'll be filling in tonight, and then as the semester progresses, more and more will come in. What's going to happen is every week you'll get a module, and it'll be called Week One module. Like this one is Week One, and it says January 12th to 11:59 p.m. January 18th, and in it will be a list of links to videos. So it'll be a list of links to videos on my YouTube channel that are optional, but they are pretty helpful. And then down below that, there will be lab related material. So as I was saying, I want to go ahead and start in chapter one. Chapter one, if you look at the textbook, it is called uh, Introduction, Measurement, and Estimating. So that's the major topic here. And what we have to do in chapter one is I first got to introduce you to the idea that in order for science to progress, we have to have some kind of system of units so that we can communicate with each other in common terms. So around the time just before the French Revolution, uh, France was a great superpower, and they sort of made us our switch to the metric system, which we now call the System International, which you can tell it's obviously got system and then the adjective coming after it, which suggests that it's a European language or something along those lines, certainly not English. And that's because it was French. So what we call SI are the international system or the System International is also called the MKS system, and M is for meters, K is for kilograms, and S is for seconds. That's why they call it that to distinguish it from the previous metric system that was more like what Napoleon came up with, or Napoleon's era came up with, which was the CGS system, centimeters, grams, seconds. There's also a system of units called the British system, which is what we use in America, and I think like the other countries like Liberia or Myanmar or something like that, a very small country, and the United States are the only two that really use the British system, including Great Britain does not use the British system. So it's really an inconvenient unit system. The British system is, but engineers are fighting. At least engineers in America are fighting tooth and nail to hold on to that system, and it's gotten so absurd that they're using things like kips and mips and bips and tips and stuff like that. And literally, a kip means a kilopound, a mip means a megapound, and a tip would mean a terapound, or a gip would mean a gigapound. So they're literally using SI prefixes, but in pounds. So it's kind of crazy. But anyways, we're not going to use that, but we do have to be able to convert units back and forth between them. So this chapter is about teaching you systems of units and systems of measurements and how to convert back and forth between them. It's also to teach you about what we call Fermi calculations by Enrico Fermi, who was actually one of his biographers called him the last man that knew everything. So that gives you some idea of how brilliant this dude was. But he basically, at the age of like 10 or 11, he found a Latin physics textbook in a local library and started teaching himself physics. And he went on to become the head of the best physics department, one of the best physics departments in the entire planet, just around the time Mussolini came to power. And he built this great physics department. Did a lot of great things, and in fact, he was able to win a Nobel Prize. And that Nobel Prize was what got him to come to America. Specifically, what happened was Enrico Fermi said, "Well, I would like to go, talking to Mussolini and Mussolini's Representatives and said, "Yes, I would like to go to the ceremony." And Mussolini very much wanted that to show that his, horribly authoritarian system was actually great. So he really wanted him to go to it. And he said, "What, I want to take my family." And they said, "No, you can't take your family." He said, "Well, then no, I'm not going." So basically, what they did is they said, "Okay, well, we'll let you go, and you can take your family because we really want you to get this award, and we really want to, be proud of our people for doing this." And he went, and as soon as he got there, he went ahead and defected to the United States, and that's why we have Fermi Lab, which is named after him, near Chicago. So Enrico Fermi was sort of, in some sense, the big brain behind J. Robert Oppenheimer and all the other people that were working on the Manhattan Project. Not that J. Robert Oppenheimer was a slouch or that Bohr or Einstein were slouches, but Bohr had limited access because of his foreign nature and the fact that he lived, he was a Dane, so he lived all the way in Denmark. Einstein, they thought, at least the Herbert Hoover and those people thought he was a security risk. So Einstein didn't get to participate very much, even though he wrote the letter that started the Manhattan Project. So really, it left all the other big brains, and there were a lot. Leo Szilard was one of the main starters that started with Einstein, and somebody else whose name escapes me. But day in and day out, they were communicating with Enrico Fermi because of Enrico Fermi's being at the head of the research. He was the first one to create a sustained nuclear reaction. He did so under the football field of the University of Chicago. And that just gives you some idea. But that Enrico Fermi was this guy that you could just sort of talk to, and he would, could tell you what seemed like random facts, but it was because he could estimate and do quick calculations like that. In the movie Oppenheimer, you'll see a guy that when they first test, they do the Trinity test on the nuclear weapon. He drops like dust or something like that, and you see this dust and leaves go like this when the explosion happens. And from that, he's able to immediately calculate in his head the total lethal output of the nuclear weapon and got it within a few percent of what the full scale calculations did. That was the kind of person he was. Another calculation he did that your book mentions is someone asked him, or he asked someone, how many piano tuners there are in the state of California or the city of San Francisco or something like that, and he could quickly come up with those type things. So we want you to be able to estimate like that. Maybe not something like piano tuners because that's not that very relevant nowadays, but still we want you to be able to do that. So you'll see some chances to do those estimates. The other thing that we want to do is, in addition to being able to convert back and forth between units and understand what the base units are, we want you to also use what we call unit analysis and or dimensional analysis, which is a way you can analyze things like, say, like the period of a pendulum. The period of a pendulum is a unit of time, and therefore it has units of seconds. And if you think it depends, for instance, on gravitational acceleration, which has units of meters per second squared, and it depends on the length of the pendulum, which has units of meters, you can write an expression just to make the units work out so that you get a formula for the period of a pendulum. And lo and behold, if you do that using unit analysis or dimensional analysis, you'll get a correct answer up to a factor of a scalar with no units. In this case, it happens to be a factor of 2 pi. But that's the kind of thing we should be able to do, not only as a way to determine whether a formula is valid, but also to come up with a formula a priori without knowing any of the actual physical mechanisms. If you can take a hypothesis as to what variables a certain quantity depends on, then you can easily generate an equation using the dimensional analysis to get it. So that's what we're going for. So I'm going to start off talking to you about the System International and specifically what it is. So the System International has a base unit, and basically there's a base unit for each type of quantity we'd measure. So for instance, you've heard or you heard me call it the MKS system. That suggests that meters, kilograms, and seconds are extremely important in the MKS system because that's the only units they actually use. And the meter, of course, is a unit of length, the kilograms a unit of mass, and the second is a unit of time. So in general, we would need a category for the base unit for mass. And even though mass is said to be, the MKS system said to be kilograms, the base unit is really the gram because kilo obviously has a prefix on it. The base unit for length is the meter, and the base unit for time is the second. Okay. Now, in that system of units, the System International, the metric system, the NKS, whatever you want to call it, it's a rational system of units where instead of having some historical facts that allow you to say, okay, there's 8 ounces in a cup, there's 2 cups in a pint, there's 4 pints in a quart, there's 2 quarts or 4 quarts in a gallon, all that kind of stuff. I think I said one of those wrong. But that's a real problem because no one makes sense of all those different units. So you've literally got to look up stuff if you're not that familiar with it. So it's not a rational system of units. In the SI system, you can take the base unit, which sometimes too big or too small. For instance, the unit of a gram is a very small unit of mass, so we don't use that often. But the unit of, 1,000 grams, which is called a kilogram, that's pretty helpful. Well, what they did is they say, okay, here's the base, and then if you want 10 times as big as the base, here's a unit. If you want 100 times as big as the base, here's another unit. And if you want 1,000 times bigger, here's another unit as well. And all those quote unquote other units is prefixes that you put on the base unit. So I'm going to start off by teaching you that, and then we're going to talk a little bit about how the base units are actually measured, because not only is it important that we all speak the same language and the same units, we all have to agree on exactly what a gram is, exactly what a meter is, exactly what a second is. And when we do that, we'd prefer to have a process where another nation or another scientist can go through and uh, develop that specific measurement itself, as opposed to having a physical object that you have to pull out, endanger the object by even taking it out, share it with other people, further endangering it, then other people taking and comparing their particular sample to that particular sample, and then fixing their particular sample, and then you take that sample back to wherever you keep it safely. That works, but it's not very convenient. And to start off everything, we had, for instance, the fundamental unit of time was the second, and that was defined to be like 1/86,400th of a day. But as we started to measure the day, which is the time between sunrise and sunrise, or between noon and noon, what we discovered is that changed by day, because the moon, for instance, is slowly drifting away from us, and that is actually causing the rate of rotation of our Earth to change, and that causes the length of a day to change. And we even have, experts that measure these things and actually add leap seconds from time to time just to correct for that so that our clocks don't all get off. But that is the original base unit for the second was 1/86,400th of a second. I think I remember that's the right number. It might have been 14,400, but either way, it's basically 24 hours times 3,600, whatever that is. Now, in addition to that, you also had a fundamental idea of what the meter was, and that was a rod that had 2 scratches on it, and those scratches were exactly 1 meter apart. The rod was made of a material that didn't corrode easily, like platinum, iridium, something like that, and they kept it in a sealed container in such a way that it was free from being able to be easily oxidized, which could cause problems, or easily change temperature in massive ways so that it could change. And we also had a fundamental unit of the kilogram, which was a little cylinder, again made of platinum iridium. But in this case, they actually minimized the surface area of it. In other words, they designed a cylinder made of, for starters, of a material that didn't easily oxidize, specifically this platinum iridium stuff. And then they did the math and calculated what the minimum parameters are, relationship between radius and height of a cylinder, what fraction or what value or functional relationship should exist between the radius and the height of the cylinder, such that the cylinder has a minimal surface area. And that's what the object is. In fact, that happens to be an extra credit question that I explain, and you can do for chapter 1 as extra credit homework, is do that derivation. Uh, but again, that gives us a physical object that represents the kilogram. And they literally have the cylinder, and it sits on a piece of wood. And then on that piece of wood is a glass dome a Leyden jar is what they call it. But you take this glass dome and you stick it over top of it, and it has a little hole in the bottom of the wood, and you connect that to a vacuum pump, and that gets rid of all the air around it, and then you seal it off. And then they take another glass dome and put it over that glass dome, and then they take another glass dome and put it over that glass dome. So all that's in an effort to protect this thing from getting harmed. But again, as I said, that's not the most efficient way. So slowly we're trying to figure out a better way of doing it. As I said, we would like a prescriptive method, some procedure that any group can follow and automatically get their own sample of what 1 meter is, what 1 gram is, and what 1 second is. We've done that with the unit of sound and we are of time, and we've done that with the unit of length, but we have not done that yet with the unit of mass, but we're still working on it. So now let me explain to you how we did that with the unit of time. So you've probably heard of atomic clocks, and you can make a clock out of cesium-137. Cesium-137 is a radioactive isotope of cesium, and cesium, Cesium 137, has this characteristic decay that occurs, and it occurs a lot. It's a random variable, but as you know, something that occurs at random, if you look over a large number of occurrences, they're very consistent. So there's small deviations over time, and in fact, when you have a huge number of individual events, they come like clockwork 100%. So, for instance, what we've discovered is this specific transition that occurs in cesium 137. It happens on the order of something like 900 million times per second. Your book actually gives you the exact number. I'm just going to make something up and say, 900 and something million. But basically, what they decided to do is they actually looked at cesium 137. They used a Geiger counter to calculate how many times that cesium 137 came in, uh, how many times that actually reacted in 1 second, roughly based on their current second. And then they made that the standard because that was so precise. It was down to like 6 decimal places on the number, I mean, on the time unit. So it was okay because they weren't changing anything. They were saying, hey, I've now locked this down to more precision than we've ever used before. So it's certainly okay to keep using this. But what it is basically you set up a Geiger counter next to a prepared sample of cesium 137. No matter where you are, it's always going to do exactly the same thing. Specifically, you wait for something like 919,546 1,362 disintegrations of the cesium 137, and every time that happens, that's exactly 1 second. And then you wait another one, that's another second. And then you wait another one, that's another second. And it's completely precise. Like literally, it's not expected to lose more than 0 point, I think there, if I remember correctly, it was something like 0.0000000000001. It's like 10 to the negative 12th is the precision of it. So basically, you're only going to lose one, what we call a picosecond per century or something like that. So that was a very precise way, and it gave us a very precise definition of the second that anybody, including alien species that we might meet from a distant galaxy, much less a distant star system, they can immediately come up with exactly the same thing that we call a second because it's a process as opposed to a physical object that they have to make. Now, once they had time nailed down that well, they could also use the precision of their knowledge of the speed of light to define the unit of distance because the speed of light, turns out from special relativity, is a constant independent of the motion of the source and independent of the motion of the observer. And that constant is in units of meters per second. The speed of light, for instance, is 299,792,458 meters per second. So that's very precise. And what they did was, at the time, they might not have known it to all, 9 of those digits or whatever. But that was more precise than they had been using. So they introduced this as the new definition of the speed of light. So now the speed of light is officially defined to be 299,792,458.0 with a bar over it. So it literally has an infinite number of decimal places, and every one of those decimal places is filled with the digit zero. So now they can use that and the definition of the second to make a definition of the meter. And what a meter has been defined as, again, assuming that I'm reciting this number for the speed of light correctly, but what you can do now is you can set up a light, like a flashlight or something like that, with a device that can measure the movement of that light, and you wait for a very specific amount of time. And when that amount of time has transpired, the light has traveled the precise distance of 1 meter. Now, what they defined it as is 1 meter is the distance light travels in 1 over 299 million 792,458ths of a second. Okay. So that's the new prescriptive definition of a meter. It's basically the distance light travels in 1 over 299,792,458ths of a second. Okay. So now that we have a fundamental unit of the second that's easily created and the fundamental unit of the meter that's easily created with the unit of the second, now we can do that as well as have a fundamental value for the speed of light. We still haven't gotten one for the mass. And of course, you'll later learn that there's other base units other than length, time, and mass. There turns out to be, for instance, either the concept of the coulomb for charge, or the concept of the amp for current, or the concept of the volt. There's different ways you can do it, but basically they came up with some base units, but other ones are just made up. Like, we didn't have to go back to the well and create a whole new unit, for instance, for velocity or speed. For instance, on your speedometer, which speedometer and the word speed and the word velocity are sort of interchangeable in everyday life. In this physics class, you'll learn that that's not the case. But either way, the fact that the units on your speedometer are miles per hour tells you a little bit of something about what speed and velocity is. It's miles, which is a unit of distance, and hours, which is a unit of time, and the word per means divide. So if you divide the distance traveled by the time taken, then you'll find the average speed. But that also tells you, hey, I don't have to make up a new unit for velocity. All I have to do is take the unit of distance and divide it by the unit of time, and I'll have a new unit called the meter per second, and that's the unit for velocity. So there's a lot of different units like that that you can make up with just the meter, the kilogram, and the second. Another one, for instance, is the unit of force, which is called the Newton. Another one's the unit of energy, which is called a joule, and another one's the unit of power, which is called the watt. All of those can be made without any other units other than meters, kilograms, and seconds. So now that we have that, I'm going to go ahead and attempt to share my screen with you guys so we can talk about the SI and how to convert units. So I'm going to share my screen with you in a second. I'm going to use my iPad. That should pop up any minute. Okay, that didn't work. Hold on a second. See if I can get it to do now. Stop share. Let me try again. It didn't work that time. That's always helpful. Okay. Now I'm going to do screen mirroring. Let's see if it works this time. Unable to connect to Williams iMac. Let's see what's going on. Do I have? It's not in airplane mode. Bluetooth is on. Wi-Fi is on. Let me check the Wi-Fi over here. Make sure I'm on the same Wi-Fi. Yep, that's the same Wi-Fi. Let's stop sharing again. I don't know why this isn't working now. It worked yesterday. Please connect to the same network as this Mac. That seems to be connected. There we go. Just had to do it 3 times, I guess. All right, so you're now looking at my screen. Those of you who had me might have had me in the past. You'll notice that my YouTube channel address has changed. It used to be slash Billy Younger Physics Solutions, but now I've changed it to at physicssolutions.com. But that's about it. So what I want to point out to you is there's a mnemonic you can use to remember the prefixes that I require you guys to know. And the mnemonic that I came up with, I'm going to warn you ahead of time that I'm still, the goober guy that's stuck in, sort of 1980s. So all my jokes are related to 1980s television shows, which none of you are old enough to remember or to even have seen probably. And I still make all my jokes about poop, pee, and booty or stuff like that. So I apologize if my mnemonics come up with something like that. But here's the mnemonic that I use, and this will all be recorded. So if you don't get it, that's okay. You can just dial up the tape on my YouTube channel and find it out. But here's the way we do the actual prefixes for the SI system. So I use this mnemonic. I say the capital T dot dot great dot dot monarch dot dot king. Notice the K is lowercase and those first 3 letters were uppercase. So TGM. And notice they each have 2 dots between them. They're important. You have to have that. But now it's going to change. So the great monarch King Henry died by, and the by comes from the fact that this is our base unit, drinking chocolate milk dot dot under dot dot nefarious dot dot people. Okay. Now, this is a big change. I used to have a questionable word there for the P, but I went with nefarious characters instead of numerous other words. But these are the prefixes for the SI. And the way it works is this base could be, for instance, yes, we're using the MKS system, and that means meters, kilograms, and seconds, but the kilogram isn't really the base unit. It just happens to be the unit that we're supposed to use in all of our physics equations. So if you have a physics equation that has mass in it, under certain circumstances, you can use other units other than kilograms, but generally it's best to just stick to kilograms because that will always work. That being said, the base unit is not the kilogram. The base unit is the gram. The base unit is the meter. The base unit is the second. And as we go further along, we'll learn of some other base units like the uh, mole is one of them. Kelvin's another one. Degrees Celsius sorta is another one, but not really. Lumens is another one, so on and so forth. But if you want to be bigger than a gram, then you can go to one prefix to the left, and that prefix represents 10 to the first power. And then if you go over, that prefix is going to represent 10 to the 2 power. And then the third one, the K, is 10 to the third power. And what that means is that capital D, that's actually the prefix called deca, and they normally write that either with a capital D and a lowercase a, or a lowercase a followed by a lowercase, or excuse me, a lowercase d followed by a lowercase a. But that's deca, and it means 10 times as big as the base. And then H is hecto, and that means 100 times bigger than the base. And then the K is kilo, and that means 1,000 times bigger than the base. Now, they didn't make up a unit for 10,000 times, so that's why the dot's there. They didn't make up a prefix for 100,000 times, so that's why the dot's there. but they did make up one for a million times, and that's mega, like Mega Mind, if you remember the old kids movie. They didn't make up one for 10 million or 100 million, but they did make up one for a billion, and that's 10 to the 9, and that capital G is giga, Giga. Uh, or if you watch Back to the Future, you might want to call it Giga instead of a hard G. You could do it as a soft G and it'd be Giga instead of Giga. And then they didn't do one for 10 million or for 100, excuse me, 10 billion or 100 billion. They just went up to what we call a trillion. That would be 10 to the 12th. And that is the prefix tera, Terra. Actually, it might be Tera, sorry. All right. Now, notice these are just like the number places. Remember when you write a number like 546, the 6 is in the ones place, the 4 is in the tens place, and the 5 is in the hundreds place. Well, the ones place is technically 10 to the 0 power. And that corresponds in this case to the base. And then the tens place would be 10 to the 1, and the hundreds place would be 10 to the 2. So it's an exact parallel to that. Now, to the right, you can shrink the base unit down uh, by the same factors. Again, it's a factor of 10, a factor of 100, a factor of 1,000, a factor of 10,000. But 10,000 is not used, so they use a dot. 100,000 is not used, so they use a dot. Then a million's used again, and then a billion's used again, and a trillion's used again. In this case, it's going to be 10 to the negative 1 for deci. That's what the lowercase d is, deci, D-E-C-I. Then 10 to the negative 2 for centi. That's, remember, an exponent that's negative means you flip the number over and then you have a positive exponent, but it's in the denominator. So 10 to the negative 1 means 1 over 10 to the 1, which is 1/10. So a decimeter is 1/10 of a meter. The centimeter is 10 to the negative 2, so that's 1 over 10 to the 2, or 1 over 100, and that makes sense because there's 100 cents in a dollar, right? That's why it's called the centi. And then the milli is 10 to the negative third, and that's 1 over 1,000. And then micro is 10 to the negative 6, nano is 10 to the negative 9, and pico is 10 to the negative 12. Oops, I wrote it a little too thin there, but 10 to the negative 12 is the pico. Now, that is really helpful in that you can, if you were taking a biology course, and I apologize, modern biology might not be like this. I have discovered that biology has become a lot more mathematical of a science since the days that I was in school. So they might not do it the same way. But in my day, when we took a biology class, they would introduce this mnemonic here. And they didn't do a mnemonic, they just give you the prefixes. And then they'd show you how you could use that to convert a number. So let me show you how you can use this setup just to convert from, let's say, gigagrams to nanograms. So let's say we have a number 0.0000000000745, and let's say that is gigagrams, and we want that converted to nanograms. Okay. So let me show you how we can use this little mnemonic as it's drawn right here to convert these units. It's not an efficient way. It was perfectly fine for biology because you had to do so little of it, but it's not good for physics. I'm just going to show it to you in hopes that it'll help you in a panic situation. So the first thing you do is you make a mark on the unit that you have. So we have a prefix of G for giga. Now, what you're going to do is count the moves. You're not going to count the places that you're at. You're going to count the moves. So if I go from giga, I want to go to nano. That's way over here. So I make a mark on it. And what I have to do is, one, I see that the giga is to the left and the nano is to the right. So I'm clearly going to have to move my decimal to the right to convert it to nanograms. Now I'm going to figure out how many places I have to move it, and this is the way you do that. So again, remember, we're counting the moves. not the positions. So I don't count the red line where the G is, but I do count the move from the G to the dot. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then 16, 17, 18. So, in order for me to convert from gigagrams to nanograms, I need to move the decimal 18 places to the right. So, I can see that this would be 3, 6, 9, 12, 13, 14, 15. Oops. 13, 14, 15. And then 16, 17, 18. So that's how many places I have to move it. So now I can write uh, equals 7, 4, 5. Now I've got to go some additional places. 1, 2, 3, 4. 1, 2, 3, 4 nanograms. And this is where the decimal is. Now, technically speaking, that is not a sig fig. Those 3 zeros I added were not there originally, so they're not significant digits. So in reality, I should write this as 7.45 times 10 to the negative 1, 2, 3, 4, 5, 6, 10 to the negative 6 nanogram, or excuse me, 10 to the positive 6 nanograms. Sorry about that. And basically, remember that's scientific notation, which hopefully everybody's already experienced. If you haven't, there's videos on it on my YouTube channel, and I'll also, just take questions at an office hour, or we can set up an appointment if you have any problems with it. But basically, when the number is bigger than is 10 or larger, then you're going to have a positive exponent. If the number is smaller than 1, you're going to have a negative exponent when you convert it to scientific notation. But does everybody see how I was able to use that figure to convert my units from gigagrams to nanograms? Now, that's not the most helpful way. In fact, the way that we use is something called the factor label method. And the trick to the factor label method is you all know that if you multiply a number by any number other than 1, you change its value. Like, let's take the number 3. What happens if I multiply 3 by 1? What do I get?
3.
3, exactly. So when you multiply a number by 1, you get the same number back, and that's an important thing to understand. But if I take and multiply 3 by 7, I get 21. That's a totally different value than 3. So that's not very helpful. When we're converting units, it's very important that we not change its value, because if we did, we're no longer converting units. We've just changed the number. So the trick is to only multiply by 1 and then to figure out all the different ways you can write 1. So the number 1, for instance, is 1, which you can also write as 1 over 1, because you can always make a number and put it over 1 to make it into a fraction. But we can be a little bit more abstract than that. We could say 2 over 2. Or we could say 3.14 divided by 3.14. Or we could get even more cocky and do pi over pi. And then it has an infinite number of decimal places, right? But the main thing is, as long as the numerator and the denominator are equivalent quantities, then the fraction is a value of 1. So let's up uh, the weirdness of this a little bit more. So what we're going to do now, instead of doing pi, we're going to be a little more abstract and use something like 1 foot is equal to 12 inches. We can also use 12 inches is equal to 1 foot. Now I think you can start to see, I did not mean to write multiply there, I meant to write equals there. Now you can see, probably see or guess where I'm headed. If I wanted, for instance, to convert from feet to inches, then if I had, for instance, 3 feet and I wanted to convert that to inches, what I would do, and this is what I've learned from years of teaching this. Sometimes my students who are taking my calculus-based physics class, they're the upper echelon in terms of accomplishments in the community college system, but still they sometimes get a little rusty on their arithmetic, especially after COVID. So what I warn people to do is when you're converting units, the number that you're converting units of, the first thing you should do is make it into a fraction. So when I have 3 feet, I'm going to make that into 3 feet divided by the number one because I'm going to be working with fractions and it'll help me to make sure I know what's the numerator and what's the denominator. Remember, denominator starts with a D and it's down in the bottom. Okay. So what I want to do is multiply this 3 feet divided by one by the number one in such a way that the feet disappear and I'm left with inches. So what I'm going to do is I'm going to put an X here and I'm going to put a fraction bar here. And I know if I put the feet on the top, I would get feet times feet, which gives me feet squared. And I would get 1 times inches would give me inches. So I'd get units of feet squared per inch. That doesn't help. So if I put the feet on the bottom, that would work better. So I'm going to use this version of the fraction. 1 foot equals 12 inches. So it's important to recognize, and maybe you already know this, but when I say a number like 3 feet, that is the number three being multiplied by a quantity called feet, which could be represented by a variable x or by an actual unit. And when you have, an x in the numerator and an x in the denominator, and there's only multiplication and divisions going on, you can cancel out the x with the x in the denominator. The same thing happens with units. I can see, for instance, that this foot up here cancels out with this foot down here, and all I'm left with is inches in the top. And 3 times 12 is 36. And then the only unit I have left on top is the inch. And 1 times 1 in the bottom, and the units canceled out, is just 1. So the answer is 36 inches. So that's the way we're going to convert units. Now, let me show you why this way is better than what I just showed you with the giga. So let's say I have 0.0000000000745 gigagrams, and I want to convert that to nanograms. What I'm going to do is immediately write that over 1, and then I'm going to multiply by 1. Now, if I look up at my giga, I know that giga represents 10 to the 9, so that means 1 gigagram is equal to 10 to the 9 grams. I wrote meter there because I'm a crackhead, but anyways, to grams. Okay. Now you can see that doing that, the gigagram cancels out with the gigagram, and I'm up to grams. Now I need to go from grams to nanograms. And what I know is that, oops, let's go back to blue. What I know is that 10 to the 9th grams is equal to, excuse me, 10 to the right 9th nanograms. That was bad. Let's kill this. So again, looking at the unit up top, I see nano is 10 to the negative 9. And what that means is 10 to the negative 9 grams is actually equal to 1 nanogram. So 10 to the negative 9 grams is equal to 1 nanogram. So now you've seen how I can use that mnemonic system to fish out an actual equivalent statement. When I made these values of 1 such that the numerator is equal to the denominator, that comes from an equivalent statement. The equivalent statement being 12 inches is equal to 1 foot, so I can make it 12 inches over 1 foot or 12 or 1 foot over 12 inches. Same thing here. Now, when I go to do this, I've already slashed from the bottom left to the top right, and it's good to keep track of what slashed with what. So now I'm going to start at the top left and go down to the bottom right. And that's what happens with these grams. And you see that now I've got the grams canceling out, and the answer comes out in nanograms, which is exactly what we want. So now I'll hit equals. And if you notice, the 10 to the 9 times the 0.000 is basically going to make the decimal come to right here. And then dividing by 10 to the negative 9 is going to make it move 9 digits further to the right. And in fact, we'll get exactly the same answer we had before. You can actually type it in if you want and get it, but you will see that you get 7.45 times 10 to the sixth nanograms. So notice that is a bit quicker than doing it the way that I showed you before. Any questions on that? All right, I got a couple of other unit conversion type problems that I want to make sure you guys understand how to do. The first one is I'm going to convert miles per hour to meters per second. Let's take, for instance, 100 miles per hour and convert that to meters per second, because that's the kind of unit we're supposed to use in this physics class for velocity or speed. We're supposed to be using meters per second because the meter is the base length unit and the second is the base time unit. So in order to do this, I'm going to use a bunch of exact conversion factors so that whatever number of sig figs I put in, I get exactly the same number of sig figs out. So I'm going to start off with 100 miles per hour, and I'm going to write the miles on top, and I'm going to make it into a fraction. So I'm going to put 1 on the bottom and put a capital H for hour. And I normally write HR just because I like to. Okay, but you can write just plain H, that's fine. Now, I'm going to use a very specific route. I'm going to use very specific conversion factors. One, because it reminds you, hey, these are conversion factors you should know off the top of your head. But two, it's because they're exact. So there's no approximation. So if I want to calculate, for instance, 100 miles per hour, to 20 decimal places, if I put in 100 miles per hour to 20 decimal places, I'll get out the answer to 20 decimal places because all these conversions are exact. So first off, what I know is 1 mile is equal to 5,280 feet. So I'm going to say times 1 mile is equal to 5,280 feet. Okay. Now, with that, I can see that the mile is going to cancel out with the mile. Notice I use the exact same slash symbol for both of them. Now, the next one, I'm going to use a different slash, and the next one, a different slash. This is just good bookkeeping, and it'll help you. So now I'm going to go from feet, I'm going to go to inches. And I know, for instance, that 1 foot is 12 inches. And now, because I've already used the slash that goes from top left to bottom right, I'm going to go from bottom left to top right. So now you can see I've got units of inches per hour. Now I want to go from inches to centimeters, and this is the whole reason I went this way, because there's an exact uh, conversion factor between inches and centimeters, and it's exact to an infinite number of decimal places. So what I know is that 1 inch is equal to 2.54 centimeters exactly. Okay, well, now I've used those two slashes, so this time I'm going to use an actual X. And now I've got centimeters per hour. Now I've converted from the British system into the metric system, at least for the distance. But I want to go ahead and go to meters, and I know that just like there's 100 cents in $1, there's 100 centimeters in 1 meter. So I'm going to write 100 centimeters on the bottom and 1 meter on the top. Now it looks like I've run out of slash marks, but here's the way I dice it up. One thing you could do is make a slash with a circle on the end, or make a curved slash or something like that. I'm going to make a slash with a circle on the end. So that cancels out with that, like that. And now we're up to meters per hour. Now I'm going to convert hours. Now notice the hours in the bottom. So in order to get rid of hours, I've got to put the hours in the numerator. So what I know is 1 hour is equal to 60 minutes. Now I could have went ahead and said 1 hour is equal to 3,600 seconds, but I wanted to show you yet another slash mark. So now what I'm going to do is go from bottom left to top right with a circle on the end. So that gets rid of that. Now I'm down to, oops, I wrote the wrong way. Take that out, take that out, take that out. Oops. Okay. What I was supposed to do was this guy and this guy. Okay. So now I'm down to meters per minute. Now I'm going to do the next step, which is going to make it meters per second. And what I know is that 1 minute is 60 seconds. So I'm going to put the 1 minute on top. And I'm going to put the 60 seconds on the bottom. And now I'm going to use another new slash mark. I've got top left to bottom right and bottom left to top right. So now I'm going to do an X like that. And that works. Okay. Now, how do we actually compute this mess? Well, the trick is you multiply each of the numerators and get a new numerator. So I'm going to take the numbers that you see in all the numerators and I'm going to multiply them. So I've got 100 times 5,280 times 12 times 2.54 times 1 times 1 times 1, and that gives me 1.609, or let's say 16,093,440 is the number that I get, and the only unit up top is the meter, so I'll put the meter by it. Now I draw a fraction bar. Now I multiply each of the denominators. So I'm going to do 1 times 1 times 1 times 100 times 60 times 60, and that gives me 360,000. And the only unit left in the bottom is the second. So now all I have to do is take that first number, 16093,440, and divide it by the second number, which is the 360,000, and that gives me 44.704 meters per second. But if I assume that all three of those digits, the 1, the 0, and the 0, are all sig figs, then I only have 3 sig figs, and therefore the 0 and the 4 are not significant. But you can keep them anyways, and you should. When you're doing a string of calculations, every time you make one calculation, if you round it every time, you're going to get a buildup of error and your number is going to bear no resemblance to the actual answer. So what you're supposed to do is keep at least one extra non-significant digit until the very end, and then at the end round it to the appropriate place. So for instance, if I use this figure later, I would go ahead and write it down as 44.70 or 44.704, but I'd keep track of those underlined marks using my significant digit rules. And then at the end, I would round it according to getting rid of those underlined digits. And then that would give me a more specific example or a better answer of what I'm supposed to have without rounding it repeatedly and screwing up the number. So what we've learned is that 100 miles per hour is about 44.7 meters per second. Anybody have any questions on that? Yes, Michelle.
So with the significant digits, which portion of that problem were you pulling that it's only the first three from? Just to
Uh,
make sure.
yeah, that's actually a very good question you're asking, and I want to explain it very well because
Okay.
your textbook says one thing. In my lab, I teach an entirely different thing, and the
Okay.
reason why is we need a definitive answer in lab. So the rules in lab are the leftmost non-zero digit of any number is what we call the most significant digit. So if I wrote, for instance, the number 1500, I also wrote the number 15.00, and I also wrote the number 0.000150, like that. The leftmost non-zero digit is the MSD. So in this number, that's the MSD. In this number, this is the MSD. And in this number, this is the MSD, which means most significant digit. Now, there's two other rules for counting sig figs. The second rule is if there is no decimal present, if there is no decimal present, then the rightmost non-zero digit is the least significant digit. So you see the 1500 has no decimal present, so we actually have to call the 5 the LSD. So definitively, the number 1500 has, according to my rules, two sig figs. And according to Giancoli, your textbook author, he calls this number ambiguous. And that's going to come up. There's literally going to be a test question like this where they're going to ask you, how many sig figs does 5,000 have on it? And it'll have answers like 4, 3, 1, and ambiguous. And your answer is going to be hopefully ambiguous, right? Now, again, the first rule was the leftmost non-zero digit is the most significant. The second rule is if there is no decimal present, the rightmost non-zero digit is the least significant. That's only applies to one of these numbers. And then the third rule is if there is a decimal present, then the rightmost digit is the least significant digit. So for this case, this is your LSD. And for this case, this is your LSD. So this number has 3 sig figs. This number has 4, and this number has 2. So that's the way we'll use sig fig rules or sig fig calculations or determinations in our lab. Now, when you take two numbers and multiply them, or take two numbers or more and divide them, then what you do is you find the number that you used in the multiplication or division problem, find the number that had the fewest number of sig figs, and that's the number of sig figs your answer has to have in it. So when you multiply a number that has 42 sig figs by a number that has 2 sig figs, you have to round the answer to just 2 sig figs. And it doesn't even matter if you multiply 50 numbers, all of which had 70 digits, except for the last one, which only has 2 digits. When you multiply them all, you're only going to be allowed to report 2 sig figs. So that's the rule for multiplication. The rule for addition doesn't use sig figs. It uses something called precision, and that basically says the number of decimal places or the number of digits that are significant. So, for instance, in the 1500 case, the least significant number really is in the hundreds place. So the smallest or the highest precision that you can get when you add this number 1500 to something else is a precision down to the hundreds place, because the 0 and the 0 are not sig figs. Therefore, they're not significant, and only the hundreds place is. So that's what we mean by precision. Precision is sort of the number of decimal places. If on the
That
other hand,
clarifies a lot.
yeah, go ahead.
No, I was just that clarifies a lot. That was what I was getting kind of mixed up on is like why does the last two digits of a whole number just get dropped? So that makes a
Yeah,
lot of sense.
if
So it's
you
really like not accurate.
exactly, if you really wanted to write this number correctly, you should write as 1.5 times 10 to the 3. That way you can show the proper number of sig figs.
Yeah, okay. That's a good trick.
Yeah, that's the way that's supposed to be done, and that's why obviously books would be ugly and it would take a lot more time to type them up if we were really strict like that. But the author would rather use numbers like 500 and 1500 and just say, hey, they're ambiguous unless I tell you otherwise. All right, any questions on that? And all these, by the way, there's videos for all of this, how to do sig figs, how to determine sig figs. What do you do when you add two numbers? What do you do when you subtract two numbers? What do you do when you multiply? What do you do when you divide? What do you do when you take the sign of a number? And the rule there is when you take a function of a number, the answer comes out to the same number of sig figs that you put in. So if you took the sine of 15 degrees has two sig figs, so you should round that to two sig figs. But you're probably going to use that for later figures, so you should probably keep at least 15 or 3 sig figs or 4 sig figs, just so you don't repeatedly round and screw things up. But then at the end, you're going to count it as if it was only 2 sig figs. Any other questions on that? All right. There's another quantity or another type of conversion that I want you guys to understand, and this is the wonderful value of the density of water, which I'm going to take the time to write a decimal there, because if you really treat it at 20 degrees Celsius, you actually have 4 sig figs here. This is the density of water, and it's 1,000 kilograms per cubic meter. And uh, the symbol for density is rho, which if you type a lowercase r and then change the font to symbol, Microsoft Word will make it into the rho, so you'll know what a rho looks like. But that's the density of water. If you wanted the density of seawater, obviously it changes from sea to sea to sea. And for instance, if you went to the Dead Sea, it would be a lot higher density. Or if you went to the Great Salt Lake, which used to be part of Lake Bonneville in Salt Lake City, if you did that, then that would be quite a bit bigger as well. But in general, what we say is the density of seawater is roughly 1,025 kilograms per cubic meter. So that's another option. But what I'm going to do is I'm going to convert the density of water from kilograms per cubic meter to grams per cubic centimeter. So let me show you how to do that. And this is a whole different type of beast that we're dealing with. I'm going to write this as 100 kilograms divided by 1 meter cubed. Now remember, a meter cubed means a meter times a meter times a meter. So that's important. First, I'm going to deal with the kilograms, and what I know is that 1 kilogram is equal to 1,000 grams. That's going to allow me to get rid of my kilogram unit and leave just the gram. Now I've got to get rid of the meter, but there's actually a meter, then there's another meter, then there's another meter. So first off, I'm going to get rid of one of those meters, and the way I'm going to do it is I'm going to say that 1 meter is equal to 100 centimeters. But that only takes care of one, and I've got an exponent of 3. So now I've got to do another one and that takes care of 2. Now I've got to do one more. And what you see now is this 3 cancels out with these 3 like that. Now you should be able to see that basically I'm taking 1,000, multiplying it by 1,000, that gives me 1,000,000. And then I'm taking 1 times 1 times 100 times 100 times 100, that gives me another 1,000,000. So it's 1,000,000 grams divided by 1,000,000 cubic centimeters, which is 1.000 grams per cubic centimeter. So that's how you deal not only with units in the denominator, but units with exponents in it. Does that make sense? All right. Now, technically, because of all that's happened, I've run out of time, so I can't show you as much as I would like to. I'm going to finish it up more next time, and you can feel free to check out stuff. What I need you to do though is very soon your Pearson course should come up. And off in the left-hand side of Canvas, they'll say Access Pearson, and you should be able to click on that Access Pearson, and then it'll allow you to go in, and if you've already bought your textbook package, you can type in your user number there. If you haven't, it's actually cheaper to buy it straight online right there. So feel free to do so. You can pay for the 1 year or 2 year option. I would definitely do a full year no matter what, because there's a good chance that you have to take 2 semesters rather than one. So definitely do that. And I'd take the electronic book because the electronic book is a lot cheaper. So it used to be around 79 bucks. I think it might be $99 now, but that would give you full access to the website and to an ebook and to homeworks and all that good stuff. If you don't like reading ebooks, I get it. What you can then do is go on eBay or Amazon or anything and find a 4th edition of this textbook or even a 3rd edition of this textbook and buy that for a couple bucks. That way you can use it for the reading of a physical text. And then if I ever give you an assignment out of the 5th edition, you can still have the electronic version to use. But I'm going to let you guys go. What I'd like each of you to do, I know one person's already left, chat me your first and last name, and then you're free to go. And we're going to do that every class. You can do that as soon as you come in if you want, but just keep an eye on that. And that's sort of how I check roll. There's other ways I can do it, but this helps me. Thank you for coming, everybody. I'll get back in touch with you regarding lab. Don't sweat it if you don't hear something immediately. And hopefully this video will be posted tonight. If not, it'll be posted tomorrow. Thanks, Michelle. Thanks, everybody, for coming. I appreciate it. And sorry for the problems that we had initially. Anybody have any questions? I'm free to ask them.
I have a question.
Yes. How can I help you, Nestor?
Uh, I was tracking during this whole lecture, and some reason my Canvas just got rid of Physics 1 as like a on my dashboard.
Whoa.
And I know in the beginning you said you were like adding stuff or you're uploading stuff. I don't know if it messed up, but when I was trying to access Pearson, it was saying it was like not able to open, or I don't
Okay.
know if it could be a me thing, but
No, I think it's on my side specifically. I just submitted the Access Pearson for your course. It usually takes a couple hours, so it's probably just not ready yet.
oh,
So
okay.
if you try
So
to click on it, it'll say like an error or something.
yeah.
Yep.
Okay. Well, I'll just give it till tomorrow then, because it disappeared out of my whole dashboard.
Yeah, the Access Pearson can't come up yet, but it'll come up very soon.
Okay. I
I'll
also have
probably
a
email you when I have it ready. That'll help too.
okay. I also have a question on this course in general.
Yes.
How does the flow of this course gonna go, as in like the workload? Is it like everything through Pearson, or is it gonna
Okay,
be?
yeah, so it's a little weird. The way my course works is you're going to have a conceptual homework and a problem-solving homework set as a bare minimum every chapter.
Hmm.
So if you look in Pearson, you'll find chapter O1 HW, which is the problem set, and then you'll see chapter O1 conceptual, and that's the concept problems. Sometimes you'll get a chapter where it'll have two sets that say HW because it's more than one set. So in that case, you'd have three sets of homework, all of which are on Pearson. But
Okay.
that's literally the only thing that'll be in Pearson is those homeworks and their grades. Everything else, which means practice tests, online tests, face-to-face tests, all of those will appear actually in Canvas.
Okay. 10
Okay.
4. I think that's all I need.
All right,
I
the
appreciate
course
you
is kind of
answering.
tough. Feel free to ask me questions. I create a rigorous calculus-based physics class, so you will actually do calculus. There's a lot of calculus-based physics courses at universities and colleges that use very little calculus. That's not the kind of class that I offer. So feel free to ask me about those questions if you have any problems. And if you get stressed out and think you're going to fail, contact me first because I've never, ever, ever recommended someone drop my class unless they literally had missed a bunch of tests or something like that. So, all
Sweet. Thank you,
right.
Professor.
All right.
You have a
You're
nice
welcome,
night.
Mister. Have a good day. Anybody else have any questions? I saw Eli or Ely. I'm not sure how I pronounce it.
Yeah,
Came.
hey, sorry, I accidentally left the class a little early. I forgot to type my name in for the role.
Okay,
Uh,
yeah, I knew someone had left. I wondered if who that was. So yeah, if you
yeah,
just type
sorry
your
about
name
that.
in the
I'll
chat.
type my name back in.
Yeah, no problem.
Yeah.
I wouldn't. That you don't lose points for being absent, so don't worry about that. But yeah, it's good to know that you were here. Anybody else have any questions? All right. Well, I'm going to let you guys go. I hope you have a good evening and pay attention to my email. It's going to take a couple of days before everything gets settled out. But I will let you know probably tomorrow about that as far as the Pearson goes, as well as far as the lab goes, because we've got to figure out something with regards to that as well. So let me know if you have any questions, and I will be here. Okay, one thing we didn't get to cover on this was dimensional and unit analysis. So I wanted to work a dimensional analysis problem real quick, just so you'd have this on the video. If we say introduce a quantity called the Planck wavelength, which is lambda sub p, we know if we want to write the dimensions of something, we write it in square brackets. Now, this is a wavelength, and that means it should have units of length, which means in terms of units, it would be the meter. But if you wanted to do this in terms of dimensions, because there's something called dimensional analysis and something called unit analysis. They're equivalent, but one is sort of more generic that can work in any situation, whereas the other one is a very specific set of units, the SI or the CGS or the British system or whatever. In this case, instead of the unit of length being the meter, we use a capital L just to represent length, and we use a capital T for time and a capital M for mass. So we know that this Planck length depends on the gravitational constant of the universe, which has units of Newton meters squared per kilogram squared. You guys don't know what a Newton is yet, so I'm going to write that as a kilogram meter per second squared times a meter squared per kilogram squared. So you end up getting that is 1 kilogram in the top and 2 kilograms on the bottom. Is going to leave just 1 kilogram in the bottom, but I'm going to get meters to the third power because a meter times a meter squared is meters to the third. I'm going to get a single kilogram in the bottom, but I'm going to get a second raised to the 2 power. Notice I just wrote the 1 there so there would be no ambiguity. So that's the actual units for gravitational acceleration, gravitational constant. If I wanted to do this dimension-wise, I would represent this as L cubed over M t squared, and you might even put a m with the exponent of 1. It also depends on the speed of light, which is given by the symbol c, and the speed of light is in meters per second, but in terms of dimensions, the speed of light would be distance over time. And it also depends on Planck's constant, which is the symbol h. And Planck's constant has units of joule seconds, which equals a Newton times a meter times a second, which again, all these values are things you're not expected to know yet. We would have to give you what units they're in or what dimensions they're in, but I'll show you in a second what that means. So the Newton is a kilogram meter per second squared, and then I'm going to multiply that by a meter because a Newton meter is a joule, and then I'm going to multiply that by a second because it's a joule times seconds. So what you see is the second in the numerator cancels out one of the seconds in the bottom, and we end up getting kilograms meters squared per second. And that's the dimensions there, and or the units there. The dimensions, on the other hand, are capital M, L squared, and T in the bottom, so T to the -1 power. So if I wanted to guess at a formula for the Planck wavelength, I would assume that the Planck wavelength depends on the big G I showed you, the C for the speed of light, and the H. So this is how I'd work it out. I would say lambda is equal to the value of g raised to the p power times the value of the speed of light raised to the q power times the value of Planck's constant raised to the L power. Now all I have to do is either use dimensions or use units and solve for P, Q, and L. Now remember, what we're assuming is it always depends on these three variables. So if I multiply them all and raise them to a power, that's the only way I could really put them all in one formula, is they all have to be multiplied / divided by one another. And that's the most general response. You could have a second term, but that would have to have the same units as the first term. And you might find out that one of these variables isn't required, but that's not the kind of problem we're trying to solve. We're trying to say, hey, if I tell you that a certain quantity depends on these variables and I give you what the dimensions of those variables are, you should be able to figure out a correct formula, or it's impossible to solve. So what I'm going to do now is I'm going to do this with dimensions because dimensions are cleaner, easier to use. So the left-hand side is the lambda p specifically that we were talking about. So that has dimensions of L to the 1 power. I don't have to put it there, but it makes it a little clearer if I put the exponent, even if the variable's not there. So there's no m's and there's no t's on the left-hand side. So the way I represent that is I'll say it's times m to the 0 and times t to the 0. That's all from this left-hand side. Like that. Now the right hand side, I do the same thing, except now I've got to take the g dimensions, which are L cubed over m t squared, and I got to raise them to the p power. So this is going to be L to the 3p over m to the p over t to the 2p. And that's because when you raise a power to a power, you multiply. So that's why I got 3p, p, and 2p. Now that's just for the gravitational constant. Now I've got to also do it for the speed of light, and that's going to be L to the q over t to the q. Now I've also got to do it for Planck's constant, and that's going to be m to the L power, L to the 2L power, and then T in the bottom to the L power. So now I can say L to the 1, M to the 0, T to the 0 is equal to, now I'm going to try to combine all the L's. I've got a L to the 3p multiplied by L to the Q, so that's going to become plus Q, and multiplied or divided by, no, multiplied by, excuse me, by L to the 2L, so it's going to be plus 2L. So that takes care of my L's. Now I've got to do my M's. I've got a M in the bottom, so that's M to the -1, and I got a M to the L in the top. So this is going to be M to the L minus P. So that's the power of M on the right-hand side. Now I've got to do the T power. Now I've got T to the -2p, T to the -q, and T to the -L. So it's going to be T to the -2p, -q, -L. So what I see is I've got 3p plus q plus 2l has got to equal 1. I've got L minus P has got to equal 0, which is really easy. So that's going to be the first one we attack. We're going to say L has to be equal to P. And now we're going to take the third equation, which is -2P minus Q minus L. That's got to equal 0 as well. So I've already figured out one requirement, specifically that L and P are the same thing. So if I put this in the last equation, take this quantity and this quantity and put them together, what I'm going to get now is -2P minus P, because L is the same thing as P, minus Q is equal to 0. -2P minus P is -3P. So I'm going to say -3P is equal to Q, because I can put the Q on the other side, and that would become positive then. And now I can see that P is equal to -Q over 3. So now I know L and P are the same thing, and P is -Q over 3. So now I can plug that in to this last equation, and I'm going to copy all this as follows to the next page. I'll put it up here. Okay, so now I can do all this. I'm going to say 3P, which we've already decided to say L is P. So I'm going to say 3, oops, gotta go back to my pen. I'm going to say 3P plus Q plus 2. Now remember, L and P are the same, so I'm going to write 2P there, and that's all equal to 1. 3P plus 2P gives me 5P, so now I'm going to say 5P plus Q is equal to 1, or I can finally say that Q is equal to 1 minus 5P. Now P we already figured out in terms of Q, so I'm going to say Q is equal to 1 minus 5, but P, I'm going to replace that with -Q over 3, which is what we found a few minutes ago. Now I get 1 plus 5/3 Q, like that. Uh, I can pull the 5/3. Actually, I can pull the Q to the right-hand side and pull the 1 to the left-hand side. I'm going to get -1 is equal to, now 5/3 minus 3/3 is 2/3. So I'm going to say 2/3 Q is equal to -1. And that means that Q is equal to -3/2. So now I know Q is -3/2. I know P is equal to -Q over 3, which therefore becomes -1 over 3 times -3/2. So that means that's going to become +1/2. So now I've got P is equal to 1/2, and we know that L is equal to P. So L is equal to P is equal to 1/2. And what we said initially was that the Planck constant is equal to uh, G to the P, C to the Q, H to the L. G to the P, C to the Q, H to the L, which now means the Planck length, the Planck wavelength, is G to the P power. So that means a square root. So that's going to be G. The 1/2 means the square root, so that's G. The speed of light is raised to the Q power, and the Q power is -3/2, so that's means it's in the denominator because it's negative, and it's a square root because it's 1/2, but it should in fact be C cubed in the bottom. And then finally, H is also 1/2, has an exponent of 1/2, so that's going to be Planck's constant under the square root, and that's our result. So that's the way you can do dimensional analysis. And in this case, I did dimensional analysis. If I did the same thing using kilograms, meters, and seconds, I would have done unit analysis, which is another perfectly fine way. But let's call it a day. That's it. Have a good day. Thanks for coming, everyone. Bye-bye.